Okay, so let's start the webinar. Uh, so first of all, welcome. And today, in this webinar, I will discuss the navigation project that you have to submit on May 14th, I think. And so I will describe what the project is, the environment is, and I will also go over this coding example in a DQN lesson, which will be helpful to you for your project. You can make some minor modification to it and solve your project, solve the environment of the project, and you're most welcome to add your own touch to it. Improve it, make it more efficient later on. So the code will help you get started with your project. So first of all, let's take a look at the navigation project and the environment, what environment we are using. So the instruction for these are here. So if you go to value based methods, click on navigation view lesson, you will be here. Okay. Now first of all, until now in the project, sorry, in the nano degree, we have been using OpenAI environments, right? OpenAI environments. We were solving OpenAI environments. Now our project is on Unity environment. So Unity is an open source environment. It provides open source environments for games and for simulation, and these environments can also be used for deep reinforcement learning, for implementing the algorithms of deep reinforcement learning, and see how effective they are, how if they are meeting the results, if they are giving the expected results or not. So if you Google about Unity, and there's a lot of information what they do. Basically, it's for gaming and simulation, but it can also be used for training, as it says here, training intelligent agents. So if you when you come to this section, it's pretty self informative. You can just go through the lessons and it will give you all information about what the project is and what you're expected to do. So yeah, this is the robotic arm environment. Yeah, but you don't need to worry about it. It's just some information about Unity, and you can check out other Unity environments on this GitHub repository. Okay, so let's move on to our project, navigation project. Okay, so okay, so you can see this GIF. There is this environment where there are bananas, and the goal of the agent is to collect yellow bananas. And when it collects yellow banana, it gets a +1 reward, and for if it collects blue banana, it gets -1 reward. So it's like a simulation for real life navigation for a robot or for an agent. If it's navigating in real life world, it's a good training for that agent. So so this so that's it. And then the space has 37 dimensions. So one state value will give out 37 variables. One state is defined by 37 variables, and it's based on the velocity, ray-based perception, for direction, and so on. And the agent's task is to select the best action possible given a particular state. So if it's here, whether it should move forward or move backward or turn left or turn right. So, and those actions are provided by 0, 1, 2, 3. So instead of just two actions, it's four actions, like softmax. you might use softmax here. And so, okay, the task is episodic, it's not a continuous task. And if you solve this environment, you should get an average score of plus 13 over last 100 episodes. And you can implement this. Some of you might have seen in the DQN code how you calculate average over the last 100 episodes. You can do it with NumPy arrays as well, but it's good to use the this collection, the dictionary from the collection library. I will go over that when I show you the DQN code. Uh, yeah, and this project is so Unity itself has an actual environment, banana collector environment, and for this nanodegree, Udacity has made an identical environment, identical to that. So, okay, so you have to work with this environment that is created by Udacity, not the Unity environment, but it's based on the Unity and this banana collector environment. Okay, yeah, it says the project submission should not use the environment from ML agents GitHub page. So Udacity has created this environment, you use that. And instruction to download and install the environment are also given in this lesson, and I'll go over that. Okay, this is something funny. So the environment, just one second, I'll just check something. Okay, so yeah, so the environment is move. If you want to play, you can go through this and notebook, and you can use WSAD on your keyboard to play in the environment. So you will know how difficult it is to, even for humans, it takes time to learn to play this environment or to earn points in this environment. So it's for you if you want to play it as a game. Yeah, couple. This will help you understand the task. Okay, this is for me, but for you it will show the actual workspace, actual code. Okay, and so if you haven't already cloned this nanodegrees GitHub repository, the instructions are here. If you go here, there are instructions on downloading this. All these environments, all these codes are in this repository. Udacity deep reinforcement learning. You can just download it, or you can download it from here or from your command prompt. And the instructions are also provided in on this page, and the instructions to create conda environments, uh, which will be good for your Udacity projects, are here. You can just create these. This is how you clone it on your Anaconda prompt. If you have Anaconda on your system, uh, you can just open the Anaconda prompt and type this, and it will start downloading the environment in your local directory. And you should, now you created this virtual environment, DRLND, right? So if you want to use that in your notebook, you can switch. You can go to kernel and you can switch to this uh, environment. Okay, so once you download or clone this repository, it will have uh, codes provided by Udacity for this nanodegree. All the codes, solution as well as the problem exercise codes for every lesson that you have done until now, and even for later lessons. Everything will be in there. Okay. Okay, so you can download that here. You can read the instructions on readme .md. This is the markdown file. Uh, and these are the instructions to download the navigation environment created by Udacity. So if you go click on these links, 64-bit and or 32-bit if you have Windows, if you have Linux or a Mac, and there's instructions on how to download the environment there. And if you are using AWS, Amazon instances to solve this environment, you can go through this link for the instructions. Okay. And if you didn't know that you can use AWS, you get $100 in credit for AWS. But you currently don't need it because Udacity has provided you GPU as well, and you can use that GPU. But yeah, you can use this AWS $100 credits even after your nano degree for like 12 months. You have 12 months for that. So if you want to check this out, you can go to the extracurricular page, and there is instruction on how to get access to that. Then when you come to this page, you can there is a silent video about the environment, and it will give you some information, more information about the environment. Okay. You don't have to do this. This is optional, building your own environment. Okay, now actual project instructions. This is where the real thing starts. So once you have explored the environment and you know how it works, all the actions, states, etc., then you will start solving the environment. And once you have solved it, once you are successful, this page gives you information about the submission. So you don't just solve the environment and then it's done. No, you have to submit this project. You have to upload your material on GitHub repository, and you have to submit that GitHub repository. And what you need to upload, all those instructions are here. So you should have a README file, which is like your face of your GitHub repository. It gives all instructions about the project, how to download the dependencies, the libraries, the frameworks for the project, and then information about the actual project, brief information, the environment, what is the environment, what are the actions, everything, how does it, what is required to solve the environment, all those information, and that will be in README file. And then your GitHub repository should also have a code. The code, obviously, you can upload your Python notebook or the Python file. Either way, it's fine. You are encouraged to upload the .py files, but you can also upload IPython notebooks. And your submission should also have a report file. So this will be a report dot markdown file or a report dot PDF file. So if you don't know how to write markdown files, there are instructions, and if you don't know, then you can just write down your instructions on a Word file and then save it as PDF, and then you can submit that as a report.pdf. Okay, so more information about this, how your project will be scored, is on this link, the project rubric. So if you go click on this, if you click on this is how your project will be reviewed on this criteria. So as far as training code is concerned, the repository, you also have option of submitting a zip file, but I encourage you to submit your GitHub repository. So the code should work it should be working code. It will be checked if the code is working, if it's or if it's giving any error or not. That will be reviewed. It should be organized code for the training agent. It should be written in PyTorch and Python 3, not the previous versions. PyTorch and Python 3 frameworks only. And you also have to submit your saved model weights that are solving the environment. Okay. Instructions for README markdown file are here. You can go over that. Project instructions, etc., etc. And we also have to submit the report. So sometimes students just submit a PDF version of their IPython notebook. So that's not it. So if you submit that, your project won't pass. You have to submit another report. It can be a markdown file or a PDF file, and it should have, first of all, it should have the structure of your networks, neural networks, outline of the neural network, what's going in, what is the input size, what is the size of the hidden layers, how many nodes, what activation functions are you using on those hidden layers, what is the size of the output layer and its activation. That should be an outline of that, should include in the report. And then how your learning or algorithm is working, what are the steps, outline the steps of your learning algorithm. And in the end, you should have a plot of the rewards, the work that solved it, and it should be solved. It should have plus 13 or more, score of plus 13 or more. And in the end, it should have ideas for future work. So what you are planning to do on this project. Maybe you can say, I will improve the efficiency this way, I will this way, that way, for this project, not for any other. You can't say that I will use it for some other kind of project. That's good, but what is your plan to improve this current project? So few words on that, few lines on that. Okay. Yeah, so just like here, as you can see, you can say that, okay, I plan to implement double DQN or a dueling DQN, or prioritize experience replay on this environment to improve it even better, or to get higher score, or to solve it in fewer uh, fewer episodes. You can include that. So that's for the project instructions. And yeah, so you should have readme code report. You don't have to upload the environment files. Okay, you already have uh, given instructions about how to download them from those links, from Udacity links here. um, yeah, it was one of these pages. Yeah, so this way, so you have already you can, so in your readme you can include this information that people can download the environment from here for all these different OS or systems, and for even for AWS. So you don't have to upload the actual environment because it's very big in size, and you don't have to do that. You just need to submit readme, the code, the model weights, and a report that describes your algorithm, how it works and what are the networks and everything, and the conclusion, and the plot of the successfully solving the environment. And there's information about Udacity workspace here. So you have been provided with GPU, but you shouldn't use GPU all the time, only when you train. So you should go through, I mean, make the code work, make it work, and then you use GPU to train it. Okay. This is how your plotted reward will look like once you have successfully solved the environment. And yeah, you can just read this and you will understand more. And not sure where to start. So first of all, read the DQN paper. Uh, the link is here. Read the DQN paper, understand, especially the part where they write about the method. Okay, understand what this DQN algorithm is. Then go over the code of the DeepQ networks, and I will do that now. But you should also go over the code, understand it, and then you can just adapt the code. You have to make few modifications to it to solve the environment, and you will get the idea what modifications you need to make. Okay, there's information about how to get help, um, and in the end you submit the project here. Again, there is all the information about what the submission should include. So go through this lesson and download these dependencies, this GitHub repository, and play with the project, start playing with it, and then adapt DQN, the code provided in the DQN lesson, to solve it. Okay, so now I will go through the code in the DQN lesson here that's provided here. Okay. um, okay, so this is the notebook. Now I'm not using Udacity workspace, but you can work on the Udacity workspace as well. And in this notebook we are solving lunar lander environment. uh, it's not the project environment, it's a different environment, so you will have to make changes that way. Okay, so first of all you install and download all the necessary libraries. Obviously Torch, Gym here because we are using OpenAI Gym, Matplotlib for plotting the rewards, the results, random. You will know why, you will use it soon. And this is a very good. I encourage you to use collections, the deck dictionary provided deck provided in collections. This deck will be used for taking average over the 100 episodes. It makes it very simple. Okay, instead of using numpy arrays, it's more efficient. So okay, first of all, this environment, uh, you make it and you look at the state spaces. So there are eight uh, dimensional state. There is an 8-dimensional state. Number of actions are 4. uh, and then you play around with it. Now I will show you the actual how the actual environment works. And first of all, we'll take a big picture look at this process, and then we will go into more details of the model and how the agent, how these functions are working. So DQN, this function, okay, number of episodes 2000. It's up to you. You can use less, more, up to you. Max T is the number of steps in one episode. Again, it's up to you. You can put it at 1000, or you can just say while true, as we have seen in uh, previous assignments for other lessons. We have used while true here instead of using max T. It's up to you. Again, epsilon start, epsilon end, and decay. So this is the mechanism. So this is for decaying, reducing epsilon slowly, uh, right? For epsilon greedy, for the epsilon greedy policy. Okay. Uh, scores empty, there is empty list. And so this deck, scores window deck, so max, so this is very useful. I encourage you to use it instead of using numpy arrays. So this will only keep last 100 values, and it will dump all the previous values, and then you can just take average of the scores windows, and it will give you the average over last 100 episodes. Okay, so epsilon in the beginning is 1, and then we will slowly decay it. So it will be decayed in the other functions later. So you start with the episodes, you get first state by using environment or reset. It's nothing new. uh, so when you use this code for your navigation project, it's on Unity instead of OpenAI, right? So you will have to, you might have to change this syntax. Okay. uh, okay, the initial score is 0, so you start, you get state, and then you have this uh, agent class. You create this agent class, and one of the methods of the agent class is act. So it will take this state as input and epsilon, and it will act on that state, and it will give out, this method will give out the action, what action to take. This action will then go into the environment's step function. Okay, so this is provided by OpenAI. This might be different for Unity. It's up, you will know. So this action will go into environment, and then it will give out next state, reward, and done. And this variable, we don't care about it, so we just put underscore. So it will give out next state, reward, and done. Now the agent class has another function, another method, which takes state, action, reward, next state, and done, and it will use it somehow to learn, and we'll go through this soon. And then you say that, okay, now the new state is the next state, and you add reward to the score, and then you loop again. And if the value of done, so done has two values, true or false, or 1 or 0. So if the value of done is true, it will break this episode and it will start another episode. If not, then it will take the value of state as the next state, and it will loop over. So you have seen this before, right? And you have seen these things before as well, how you take mean of last 100 episodes, and if the environment is solved, you say, okay, the environment is solved in so many episodes. This is done before. So let's go through the other, the classes. So first of all, uh, I will show you what we discussed last week about the DQN method, how it works. So quickly I will show you the PowerPoint for that. Okay, so we discussed this last week. So quickly I will go through that. So first of all, the environment provides a state to the agent. Then the agent, based on epsilon and its epsilon greedy policy, selects an action, and then environment gives it another state. Then the agent will store the tuple state, action, the reward, and the next state, and in our case done as well, in a replay buffer, in a buffer. And once, and it will do it for every time step. It will keep storing these um, tuples, and once the size the number of tuples here are more than your batch size, the agent will sample randomly some tuples from this replay buffer based on your batch size, and it will learn from those tuples. Okay, so how the learning takes place. um, yeah, So there are two identical networks: target network, local network. And first of all, target network is used to estimate q st plus 1 at plus 1, so the action value for next state and action pair. We use that to compute q target. We use the current version of the network, local network, to compute q expected based on STAT. And then you update the parameters of local network, you train it in order to reduce the difference between q target and q expected, reduce the loss. And then you soft update the target network. So I will show you how this has been implemented in the DQN code. Okay, so let's first take a look at the model that the networks used. Um so it's identical, the two networks are identical, so we have just written one network. Okay, so first of all, the network has is a nn dot module object from torch. And in here you will see this first line. So this allows you to inherit the functions of the parent nn module. So the q network class will inherit the functions of all the functions of this nn dot module, and it will be useful to you to use all the functions of the torch nn dot module. So that's the point of this line. Okay, so you write this network. It has it takes in it has one linear layer, fully connected layer, takes in state size, and this hidden layer, the units of the first hidden layer. And then it has second layer and third layer, and the output is of action size. In this case it will be 4, I guess. Yeah. And how the feed forward works here is that it will take state. So when you input the state to this network, the feed forward is what runs it, right? This is the feed forward function. So state is taken as input. It goes through the first layer, self load fc1 here, and then ReLU activation is performed on it. So that's your X. Then this X will go through the second hidden layer. Again, there will be ReLU activation on it. And then it will go through the third layer, but there is no activation here because we are sorry, because we want to find the action value, right? So it can't be between 0 and 1, or it can't be between -1 to 1. It can be anything, any value, and we will find the max value, and then we will choose actions which has the max value. So the last layer doesn't have any activation. It just gives out the the action value given this state, qstat given this state. Okay, so how is this used in here? Okay, so this is the DQN agent class. All the functions of the agent, all the methods, all the attributes are defined here. And it also uses the network, the model that we just saw. So first of all, you import all the libraries, everything. You define these hyperparameters. You are most welcome to change this. Update every is 4. So how often, after how many steps you want to learn your agent wants to learn. That's what you define here. Again, you can change this. You can change all this. So buffer size is 100,000. You can make it 1 million. It's up to you. Batch size is 64. You can change it to whatever you want. You can play with this. Even these parameters. So LR is the learning rate. You can make it 0.0001, 0.01, whatever. Play with it. Okay. Device. So here this is the function for the CUDA, the GPU. So if GPU is available, what this says is if GPU is available, the device is CUDA 0. That's what the device called in your environment, in the Udacity environment. If GPU is not available, use CPU. That's it. That's the device. So sorry about that. So let's see how the agent. First of all, you will define all these networks. So Q network local. So that this will be your local network. Again, it is an instance of your Q network class that defined your model. And the target network, again the same, another instance of your Q network class where you defined your model, because we want them to be identical. This is the optimizer function from Torch, from PyTorch. So as you can see, we didn't define this optimizer function method here. We just said that the use use this function and take input parameters as the network locals parameters here. Okay, we didn't define this because we when we defined our network, we said that the parent use all the functions of the parent of the module. So when you create an instance of this here, it can use all the functions of NN module. So optimizer is one of those function, optim.item. Okay, so you use you're only training the Q network local, right? Target is just for as a standard, right, as a benchmark, but you are actually training your local network to generate actions. So only its parameters are fed here, and learning that it is LR. Again, you can change this to whatever value you want. So this is very important to understand. Two identical network, but we only train the local network. Okay. Self.memory is an instance of the replay buffer. You can check out the replay buffer class for more information how it's storing all the tuples. And I encourage you to read go through the code and then try to create it yourself. You'll learn a lot from there. And it will also have functions to sample from those tuples. So replay buffer has some good code in there. Okay, so these are the functions: step, act, learn, soft update. Replay buffer is so here already. So let's go to our Python notebook and go see how step by step it uses these methods of this agent class. Okay, so we are here in again back to our Python notebook. DQN, this function. Okay, again, so the environment creates a random state, and the agent will take this state and use the method act to create action. So let's go to agent.act here. So agent is an instance of our DQN agent that the DQN agent class that we created. Okay, agent is just an instance of the DQN agent class. So it will take state and it will use the method agent.act. So let's go to that agent.act. So it takes state and default value is 0, but since you mentioned EPS here, it will take the first value as 1, right? And it will take the actual value of the epsilon as you proceed in your training. If you didn't include here, then it will always be 0. So it's useful to include EPS here in this function. So act. So what it does is takes the state. Now the state that you get from OpenAI is is a NumPy array. So you have to convert to torch tensor. So this is the line that does it. So this converts the NumPy array of state, makes it into float, and un unsqueeze 0. This is a function to add a singleton dimension, um, and then it will send it to device. So if you have GPU, this information, this tensor will be sent to the GPU or CPU based on whatever you have. So this will create a state tensor from the NumPy array, and you set your local network in evaluation mode. It's not in training mode currently. It's in evaluation mode. So it just passes the state through the network and it takes the output from it. Okay. So no grad again because you are not training, and then you run the state through the network. You get some action values. So these are not actions. Okay, these are action values corresponding to those actions. As we saw in the network, we didn't use ReLU, didn't use any activation. Just it just gives out some action values. So this will give out 4 action values, right? And then you set your local network to train. In case you want to start training from the next step, if it fits that condition, then it should train. So you set this to train. If the if you are not training in the next step, when you come to this function, it will again set it to evaluation mode, so it won't train it, right? So that's why these two aligns. uh, so based on your EPS epsilon, you will either select the max. You select the action which is which is corresponding to the max action value, or you will select a random action. So at first, when your epsilon value is high, like it's close to 1, when you randomly select a number between 0 and 1, this is what this function does. It randomly selects a number between 0 and 1. So when your epsilon value is high, those random numbers will be will have a high probability of being low, less than 1. So there will be high probability of selecting a random action instead of selecting uh, the argmax. So only if this random is greater than epsilon, which will happen when epsilon is very low, uh, it will select a greedy action. So that's what we want. When the epsilon is low, when we want to exploit, when the epsilon is high, we want to explore random actions. So that's what these lines of code do. So if the random number is more than epsilon, that means epsilon is very low. It will select greedy action based on this uh, action values we got here. It will use argmax, that is, it will select the index corresponding to the highest action value, and it will send it to CPU now. Okay, and else it will select a random action of size of the action size, whatever the action size is. And yeah, so that this is what this agent.act does. So again, environment gives state, agent acts, uses its act method and gives out an action based on uh, whether it is a greedy or a epsilon greedy action. Now the action will go to environment, it will take step, and it will give out this. Now the agent class, the agent, which is an instance of the DQN agent class, it will use its method step, and it will use these parameters as input. So let's see what this step method does. So we are again back to this agent class, and we have created an instance of this class as our agent, and now it will act step. So it will use step method and takes these parameters. So first of all, what it does is it adds this new tuple that we got as input. to the buffer, the replay buffer. Self.memory again is an instance of your replay buffer here. So first of all, what it does, it adds this to a replay buffer. Then there are conditions. If you have if you are updating only after every 4 episodes, it should meet this condition, and this should be 0. If it's 0, then it will check if the replay buffer has enough tuples, if it has tuples more than your batch size. So again, it's up to you what batch size you want to choose. um, Again, it's up to you what condition to put here. Again, it's up to you what condition to put here. It's up to you. So once these conditions are met, the the agent will sample a tuple from buffer, your replay buffer, self.memory, and it will call it as an experience. So again, this experience will have these uh, 5 values, right? So it will sample experiences from your replay buffer, and then the agent will use its function learn and take experience and gamma as the inputs. Now let's see what learn does. So experiences, now again, it's called experiences, it's plural, because based on your inputs of the replay buffer, it will sample multiple tuples, right? So if you see here, depending on what the batch size it will sample those many numbers of tuples together. They are called experiences. So and then it will use the method learn. So let's go to learn, and gamma is the discounting factor, obviously. Okay, so the experiences contain states, actions, reward, next done. So it's again, it's plural. So the state is not just one state, it's a stack of states, stack of actions, stack of rewards. So it's consider them as columns, and there are multiple states in its column, and the actions corresponding to this state, and then rewards corresponding to each state, etc., etc. So these are stacks of states, action, rewards. So these are stacks of tuples together. That's experience. And your learn method will work on them together at the same time. So it's not just using one tuple in one step, it's using all of them in one step. And instead of using a for loop, we are using matrix calculations here, because they make it easier, make it faster to compute multiple inputs at the same time, right? So let's go to our main task. So first of all, you have to compute the Q target next, right? As we saw in that PowerPoint slide, it will use next states, and it will compute a action value, right? And we have to choose the action value which corresponds to which is the max, right? So that's why there is this max here. And feel free to Google these, what these functions do, unsqueeze, what these do. uh, these are all PyTorch functions. So feel free to Google these and write down, you can write down the explanation here what these do. So for example, what unsqueeze does is it adds one singleton uh, singleton dimension to, suppose it's if it's like this, so it will, unsqueeze will make it like this. So feel free to Google these other what these other methods do. So now you have Q target, which is the maximum action value given next state. You have to use this to compute your TD target or the Q target, right? So use rewards plus gamma times Q targets times 1 minus done. So what is the use of this? So done, value of done is either 0 or 1. So suppose if the done value is 1, that means there is no next state, right? So this all should be 0. You shouldn't use the action value of next state. You only use the reward you got, but you shouldn't use action value of next state. So when it's the last episode, done will be 1, and this will become 0, and automatically it will make this term 0. Anyways, so and if duns are 0, that means it's not the last state, and then it will compute this sum. Okay, once you get q target, now your next job is to uh, compute q expected. Now q expected, again, as we saw in the PowerPoint slide, it will use current state and current version of the local network, and it will give out the action value, the max action value. Okay, again, Google this, you will understand what this does. It's good to learn that way, by reading the documentation and understanding it. Okay, so and now your job is to find the difference between them, compute the loss, and what these do is they just optimize it. They will just optimize the local network to reduce the loss, and that's your one step. And then you will soft update this. So so what soft update does is it updates the target network slowly, after slowly, using the tau value. So if you see here, this function, these are all self-explanatory. It will take the parameters of target and local, and uh, it will make the parameters of target network uh, some percentage of local network. Suppose tau is 0.01, so it will make it uh, the target network becomes 99% of its own self and 1% of the local network. That means, this means that you are slowly changing the target network parameters to local network parameters, right? So go through this, you will understand it. So this is one step. So again, what we saw as a recap: take state, act, use the act method, take this action, use the act method based on your epsilon, it will give out actions, give this action to environment, and then use this to uh, learn. Okay, either, so first you add this to replay buffer, and then you learn from them, and then uh, once you have learned, your state becomes next state, and again you loop over it. If done is 1, it will break and start new episode. If not, then it will keep looping. Again, it's up to you. You can use while true here, or you can use max t here. Again, it's up to you what values you want to use here. Play with it. Again, it's up to you what value of gamma you want to use, and all these hyperparameters, you should play with it. So, and this, we have seen this before in previous assignments, previous lessons, and then it will train it. I will encourage you to put this in separate lines, so that you can individual, like separately, test if this all this syntax is correct or not. So I will put this in a separate line and put the plot also in another separate line. And you can see here, this is also saving your model. Okay, so this is the syntax for saving the model. Okay, again, you can make conditions here that save the model after every 100 episodes, or after every 50 episodes, or save it after every so much score. It's up to you. Play with it. So that's it. So that was the, it's very simple, very simple code for DQN network. You have a model, and it is used by agent, and then the agent will be used by your uh, main function for training, and then you plot the outputs. So you can use the same code, you can adapt the code, make few changes based on the environment, or you can also make changes to improve it, implement DQ, double DQN, dueling DQN, prioritize experience replay, all those things, and improve it, play with it. So, so very simple, and it's good to understand the basics of this network. Write down explanation about all these lines, because in future projects you will have to use a combination of these, so you will know more about it. So it's good to understand really well how these classes are working, how these each of these methods are implemented, and how they are working. Okay, so that's it from my side, and it's almost 1 hour. So yeah, so I will end the webinar now. And thanks for watching this as a recording or live. And good luck with your project. And always you can ask me anything anytime uh, about the project on Slack channel. So thanks for watching this. Bye.